Okay, here is example 2 for class 16 in rigid body kinematics acceleration analysis. And you can see that I've dressed up for the occasion in my Kappa Pi Sigma hat up here in my guitar room. And I wanted to include the video up here so that I could use a ruler to show the motion of this connecting rod. So I'm going to do this problem a little bit differently from some of the others, and I will write on the screen a little bit, but mostly I'll use the animations to reveal the calculation procedure. All right, so this is an engine or kind of a compressor. It doesn't matter, something along those lines. It's a reciprocating machine. And so we have a piston connected by a connecting rod to a crank shaft. In this case, it's a disc, so that the connecting rod is pinned at A, and that disc is rotating at 3 radians per second clockwise, and it's increasing that angular velocity by 8 radians per second squared. And in this geometry, point A is directly above point 0, and the angle formed between the connecting rod and this center line right here is 30 degrees. And with the dimensions that you see here of 200 millimeters radius of that disc, 400 millimeters. We could find from that, by the way, we could find that that's the 30 degrees. And often in problems, that geometry might be something that might be a first step that we might need to calculate out. Sometimes that could be annoying, but this is a right triangle, so that makes it easier. And we want to find the angular acceleration of this connecting rod AB, and probably most typically it would be something we'd want to find the acceleration of B. So one of the first things we need to do in any problem along these lines, any acceleration problem, is to do a velocity analysis first. So the disk velocity and acceleration analysis, we'll march through this because we know this information, we know these basics. We could find what the tangential acceleration and the normal acceleration and the velocity. Of course, the velocity is always tangent to the path, so the velocity is also tangent. So we find that velocity at A from just omega r, right? That's easy enough, and it's completely to the right, so it's traveling at this instant horizontally at 0.6 meters per second. And the acceleration of A right there in the normal direction is pointing towards the center at omega squared r. So 1.8 meters per second squared downwards. And then the tangential component of acceleration at A is alpha r. And that's 8 times 2, 1.6 meters per second squared. The idea in problem solving here is that we're going to try to define all the things that we know, and we can find out quickly and easily. We can find out the information about A. Then we can march through the mechanism here, the structure, and then start trying to piece together what's taking place at each of the different parts. So we got the disc out of the way. Let's move on to the rod. And for the rod, we do want to do a velocity analysis first before we do an acceleration analysis. And we find this is a kind of a niche case, a one-off, where when drawing the thing out, we'll quickly find that these velocities at A and B are parallel to each other. And we could try to work through, okay, is there any way that this thing actually has rotation? And so at this instant, right, this thing is traveling, and the camera makes the thing go backwards, so I'm sorry about that. But I'm making the thing go in the same direction. It's just the camera has reversed the thing, and that's nice, isn't it? Anyway, so the or maybe it's my fault. Maybe I should make it aligned with the thing. I guess, is that wrong? Is that back? No, that's correct right there, right? So it is moving this away right there. Yeah, so you see this thing, it's moving in this direction right there. It's traveling, right? The instant before it reaches this spot, it'll have some rotation, right? It'll be moving and getting into that spot right there, and then at the next instant, it's going to start rotating in the other direction, right? So in essence, it has reached this one spot where it is no longer has an angular velocity in either direction because it's about to change, right? It was rotating, and then it gets to another spot, and then it's going to start rotating the other direction. Okay, so that's the reason why it can pause. I think I would, when seeing this, would be skeptical as soon as I start to say, well, wait a minute, how's that thing not rotating? Well, it's in between the transition where it's rotating one way and rotating another. And by the way, me making all these hand gestures was the reason why that you see my ugly mug, my ugly shaven mug. The beard usually protects me from being able to see this part of my face. So anyway, we come to the conclusion that these velocities have to be equal to each other, so we know the velocity. And we also come to the conclusion that omega of part AB is equal to 0. Now we can go do an acceleration analysis of the rod, and we do it with the 3 diagrams. We already know the acceleration at A, that we got up above here, right? We see that we called it the normal and tangential, but we also know that they were aligned with the x and the y. So we'll go ahead and just substitute those, knowing what they are. And because we know A, we're going to set up the equation for B. Right, so it's this spot that we're actually writing an equation for the B portion of the thing. So we say the acceleration of B, which we know is either to the left or the right, is going to be equal to the acceleration of A, right? So this is because that's the reference. So we move the acceleration of A down to B, and then we pin A, and then we see what the rotation is going to be. So here's the 2 different portions of that relative acceleration, the tangential and the normal. And we were careful to draw these on here. Now, we don't necessarily know, well, we do know the omega AB is equal to 0. Right, because we found that up above from a velocity analysis. But we don't necessarily know the direction of this alpha AB. So in this case, I chose it to be in the counterclockwise, aka positive direction. So we break this. So we've written out this equation. We've drawn our diagrams, and then we start breaking it apart. We go in the y direction first. That's a good strategy here because there's nothing in the B. At B, we know that's going to be equal to 0 right there. So there's 0. We come over and we look in the y direction, and we know that this is a negative 1.8 that we got from up above, right? That was the up here, right? That was the 1.8 that we got. And then the tangential component right there is, as we've drawn it, is in the positive direction, right? So this is going upwards in the y, but we want to make sure we only use the vertical component. So it's the component of the component. That's the confusing part that students struggle with, right? So you really want to try to grab a hold of that and remember it when you're solving a problem, that you want to get the component of the component in this case. And so here is the y component of the tangential component, right? So we get that there's going to be the alpha AB times the length right here, which is the 400 millimeters or 0.4 meters, and it's going to be the sine of 60, because you could see this angle right here is going to be 60 degrees, right? And we know that because of this angle being 30 degrees right up here, we could figure out that that's 60 degrees. So finding that angle right there is an important step that we got to make. And then from that, we're able to find what alpha AB is. And now that we know alpha AB, we're able to come back into here. And that was one of the things that we were setting out to do in the beginning up here. And we found, by the way, we found that it was a positive value, so we chose correctly right up here. And now we can get the acceleration of B in the x direction right up here, right? So, and that it's completely in the x direction. So we take this portion right here, right? So that was of A, right? That's the reference. It was moving right in here. It's the tangential. It was the tangential of this guy up here. Now it's only that direction. So that's 1.6. Again, we got it from up here. And we take you notice my nomenclature right here. I'll often write that out. That's a good way to try to emphasize as an in-between step. So I didn't do that, I think, in the previous example or the part 2 of the previous example. But that's a really good thing to put in there, just to double check and really hammer home and remind yourself that you're taking the component of a component. And so that is getting in the way. We take that angular acceleration that we just found, and we multiply it. So that's alpha r, and then only the component. So now it's going to be the horizontal component of this. And we also note that I put a 0 in here to remind us that the normal acceleration was 0, and of course, remember that was because we found from here that there was no angular velocity, right? So we're able to find the value, and it's a positive value. Of course, it would be all the other things were positive, so that's the answer. So hopefully you're able to follow this. This has been a simplified problem because it was the niche situation, and it was really because of the orientation of this connecting rod that made the thing so it didn't have any angular velocity. But I was thinking maybe I should make this the first example, but I decided to make the more general case instead of making this particular one. So we'll get to another video soon. So I leave you with a little bit more guitar right here. Okay, so I'm going to start playing other guitars aside the Van Halen guitar right here. So I want to do Eruption, which is a classic thing that a lot of 13-year-olds know way better than I do. That's enough. Oh, sorry. I don't know. That was stupid. So we're done.